All right. Well, thank you, Dr. Perchy. Thank you, everyone, for the opportunity to speak. My name is Dr. Gupta, Neel Gupta. I'm actually a musculoskeletal radiologist at Tulane. I want to thank my co-authors, Aaron Yu and Dr. Nguyen, who's kind of a mentor to me. I've known him for many, many years, and I respect him, and we work well together. So my topic today is understanding deep learning networks made easy. I'll give you a quick overview on this topic. Move this out the way here a second. So today we're going to describe the general principles of artificial intelligence and machine learning, deep learning. We'll discuss the basic architecture of a neural network, including artificial neurons and network layers. We'll explain the concepts of activation, function, forward propagation, and back propagation. We'll describe the concept of steepest gradient descent to minimize output error in the process of improving the performance of a network. And we'll go through some of the training and learning process of a deep neural network. So first and foremost, let's define artificial intelligence. So AI, artificial intelligence, is a branch of computer science that is concerned with building computer systems capable of performing tasks that typically require human intelligence. And AI relies on algorithms to achieve this result. So what exactly is an algorithm? So an algorithm is a set of instructions that a computer can execute. A complex algorithm can be built on top of multiple other simple algorithms. And then many AI algorithms are capable of learning from data and thus improve themselves throughout the process. Other basic AI terminology, which we need to define, will be input data, output data, and label data set. So input data is the raw data set, which is analyzed and processed by the algorithm. An example would be medical imaging. The output data is a result of all these algorithmic calculations through which the input has been put through. An example would be image categorization and classification. Now, label data set, every data in a data set is recognized throughout the algorithm, and it can be designated by certain labels. One example would be labeling data would be malignant versus benign tumors. The variety of learning styles of an algorithm: supervised learning, unsupervised learning, semi-supervised, and reinforcement learning. So supervised learning, as it stands, is the data is labeled and specific expected outputs are obtained. Unsupervised learning, the data is not labeled, unknown, and the outputs are not known either. Semi-supervised learning is a combination, a mixture of both labeled and unlabeled data sets, and the algorithm generates results based upon the structure of this data, which is put through the algorithm. Now, reinforcement learning, the input data is unlabeled. The machine, which is the algorithm, is trained to make specific decisions. The machine is exposed to an environment where it trains itself continuously, utilizing a feedback loop. So what are the capabilities of AI? Some major capabilities include reasoning, problem solving, knowledge representation, planning, language processing, perception, motion manipulation, and machine learning, which we're talking about today. So what exactly is machine learning? So machine learning is a subset of artificial intelligence, an application of AI which can automatically learn from experience. It's built upon an algorithm that uses a variety of methods to learn information directly from the input data without relying on a predetermined equation as a model. Involves algorithms that adaptively improve their performance as the data available for learning increases. So practical applications of machine learning. Some things that come to mind are image processing, computer vision for facial recognition, motion detection, object detection. In terms of medical field, REM, computational biology for tumor detection. One example would be like a automated pap smear cervical cancer screening. So we talk about different tribes of machine learning. The 5 tribes are symbolists, connectionists, evolutionaries, Bayesians, and analogists. So what is the most relevant to radiology? And the one we talk about today is going to be connectionists utilizing backpropagation for machine learning. So Connectionist Principle can be described as an interconnected network of simple networks. Neural networks are most commonly used in the Connectionist model. And these computing systems are modeled after human brains. So such systems learn to perform tasks by considering a variety of examples. And deep learning is a framework within this connectionist principle utilizing backpropagation. So we look at deep learning. So we have AI, which is the big circle, machine learning, which is a smaller subset, and we have more specialized subset, which is deep learning. It's an AI function that mimics the workings of humans thought process. I'm sorry. It utilizes a hierarchical level of artificial neural networks built with multiple artificial neurons through a variety of layers. They're a really complicated topological network. This neural network reflects the algorithm of the network in processing and transforming data. So the word deep within deep learning, which again is the most specialized subset within AI and machine learning, refers to the number of layers. The more layers you have, theoretically, the better the output would be with the algorithm. Deep learning algorithms propagate a variety of data, the input data, through multiple layers of neurons, passing through a simplified representation to the next layer, and the next layer, the next layer, resulting in the output. Again, these algorithms are capable of learning from the variety of input data to improve performance over time. So this is what I mentioned. You have this big purple or pink circle, which is AI. And then within it, you have a small blue circle, which is machine learning, a smaller subset, and you have more specialized subset, which is deep learning. So keep this model in mind as we move through the conversation. So artificial neuron versus biological neuron. So the artificial neuron has a variety of inputs leading to an output. The biological neuron, we have excitatory and inhibitory potentials leading to an output. Scroll a little bit here. So the artificial neuron is the basic elementary unit of this artificial neural network. So another name for artificial neuron will be a node or a unit. This neuron can receive multiple inputs from other neurons, and the neuron combines the inputs and provides an output. So you look at this model here, you have three inputs here, resulting in this artificial neuron, resulting in the output here. So if you look at this model, the way that it is, there's really no control of the threshold for activation to yield the output. The output can be quite low, it could be quite high. Again, there's no control of the value of the output. So the actual artificial neuron is usually modified to have much more flexibility. So let's show how to create a practical and a really useful artificial neuron. So here we have a picture of an artificial neuron. We have multiple weights from the input. So each input, which is the raw data, which is input into the algorithm, has an associated weight, which is a parameter assigned based upon its relative importance to the other inputs. A larger weight value will have a much more influence in the output, which makes a lot of sense. A weight value near zero will produce really no significant change in the input. And then bias is a parameter in the neural network, which is used to adjust the output along with the weighted sum of the inputs to the neuron. So that's applied to the artificial neuron. And the sum signal is a combination of the weighted inputs plus the bias. And it can range from a large, really negative number to a large positive value. Again, there's no set bounding the output. The output can be quite large or quite low. And then the sum signal is passed on to the activation function, which is a dampening mechanism. And this provides a mapping mechanism between the inputs and the output of the neuron. So what do you mean by referring to the activation function as a mapping mechanism? And how does it modify the sum signal from the neuron? So let's look at this cartoon again. We have a variety of inputs which have different weights. The weights can be significant or not so significant depending on the value. Resulting in artificial neuron, we have bias, and then we have a sum signal, and the number could be quite large. So what do we do with this number, and how do we improve it so we have a more functional output? Again, the summed output signal can take a wide range of values from being really negative to really positive, and then it can grow so large that it renders the network to be completely unstable. So we need to stabilize the network. We need to apply an activation function, which is a damping mechanism to stabilize the network and result in an output which is usable for us. So the activation function, again, acts as a damping device, limits the amplitude of the output of a neuron from 0 to 1. So let's look at this graph here. We have the y-axis to be output function, the x-axis summation of all weights and biases. And we have a non-linear curve, which is a sigmoid function. This popular activation function, again, is a sigmoid function, which appears as an S-shaped curve. The dependent variable, again, the x-axis, can take on a range from a negative infinity to theoretically positive infinity. And as the summation approaches a very large number, the output is closer to 1. As the summation approaches a very large number, the sigmoid function, nonlinear function, approaches 0. So the sum signal value is mapped to a restricted output range. Okay, and the sigmoid function again maps a wide range of values, sum signal to the output of the neuron, limiting the output between 0 and 1. So we have a non-linearity kind of function or graph of the output. So how are neural networks constructed? So we have a picture here showing multiple artificial neurons in a random kind of distribution. So these neurons are put together in a variety of layers. As the algorithm is much more detailed and complicated, we have multiple layers for the data to be input to result in the output. And we have a variety of connections as depicted by these arrows. The connections are formed between neurons according to the algorithm that we're utilizing. So design the network can be modified to handle much more complicated tasks. This is achieved by adding more neurons, more layers, more connections, and new connections can also be formed according to the requirements of the algorithm. So we have the input layer, which is the dark blue, then we have multiple hidden layers, which can be numerous. Then we have additional layers, and then we have the output layer. So how will the network perform and achieve desired results? So we have to train the network. The network is not going to know what to do offhand. It's got to be trained. So untrained neural network, which is a newly designed and never been used, is really like an unexperienced performer, someone who has no idea what they're doing and how to do it. But over time, with practice and application of principles, the performer will improve. Same like the algorithm. The more data we put in, the more connections, the more backpropagation we utilize, the results will be, true to the real result that we're trying to achieve here. So the algorithms in the network must have real actual experiences of the intended task through exposure to a large amount of data. And by training the network on relevant data sets, we seek to improve performance over time. And we measure performance by monitoring the error. We want the error to be as close to 0. Initially, before rounds of backpropagation, the error will be quite high, but as through this feedback loop, the error will be reduced and we'll get a better value with the output. So let's look at this. How is a network trained? All right, so we'll use a simplified network, which is basically has a small amount of data input, a few layers in the output layer. So again, each neuron has its own bias. And we'll see that here on the note. All right, so we applied 4 different biases to 4 different artificial neurons within the hidden layers. And then we have multiple different weights. So the connections with the arrow we have here showed multiple different weights. But here the network is ready to receive training data. The training begins with feeding the data set to the network. So we have an axial DWI image of the brain demonstrating, obviously an area of restricted diffusion, suggestive of an area of vascular insult. So we know, 100% there's a vascular insult here. So we want to see what the network will provide, what kind of information, what kind of output we'll get here. So the data is sent to the input neurons. The data will propagate slowly throughout the network. Again, we have multiple weights and biases and connections here. Then each neuron is activated by the effects of the input plus the weight and bias, and the interaction of the neurons will yield an output. So with this here, we have an output 40% probability image contains a stroke, 60% probability image does not contain a stroke. So we have a high error here. So how do we minimize this? Again, we're utilizing the algorithm. Again, our output is not equal to the true result. We have a high error here. So the error is calculated to be true result, which is 100% minus output, which is 40%. So the error is 60% here. So we have to adjust the network to minimize error, which is effectively improving the performance of the network. So we're using a common technique in the deep learning network to minimize the error. We'll send the error back through backpropagation into the network. And then we're going to adjust the weights and biases. So this technique is called backpropagation, employing an algorithm to adjust weights and biases. Each connection is now updated with new weights. And each neuron has new values of a bias. And then these alteration of weights and biases will work to minimize error in the system and in the network. So backpropagation, which is part of the connectionist principle for machine learning, is an essential mechanism by which neural networks learn. It's a smart algorithm and looks for minimal value of the error in changing weights and biases. It gets its name because the weights and biases are updated backwards from output toward input. It utilizes a mathematical operation, a calculus-based operation, or gradient descent, which is basically adjusting weights and biases constantly to minimize error. So what is the concept of the gradient descent? So we have it's a mathematical operation that computes the gradient, which is rate of change of error. So we look at the two pathways down here. We have two dots and we have multiple red arrows. So utilizing the gradient descent, we have a nonlinear function, nonlinear pathway, which will be the kind of shortest and most direct pathway to minimize error by changing weights and biases. On pathway 2, we have more of a linear manifestation here, showing more of a prolonged approach to minimize error. So with gradient descent, it seeks the path to reach the minimum error most quickly and efficiently, as we see in pathway 1. Whoops. This just basically shows you how it's a calculus-based process of changing the weights and biases to minimize error. Another graph, we show sort of surface function rendering. We see the most direct and the shortest and most quick and efficient way to minimize error. So what's next? We will train the network with more data sets. The more data you put in, the more connections, theoretically, the more higher quality output you receive. So each time a new data set is run through the network, the backpropagation algorithm will improve the performance of the network. The gradient descent algorithm updates the weights and biases towards a smaller error. Again, the network continues to learn and improve its predictive output here. So how does our network recognize shape here? So we have a network here. We have a variety of shapes, triangles, pentagons, square. Basically, the input layer is a digitization image of the shape into pixels, and the pixels are fed into the input layer. Again, we have multiple connections, which are weighted. This layer, which is the pink circles, recognizes these pixels being bright or dark. And then we have the hidden layers. This layer, which is in blue, assembles the edges. The next layer places the edges into a form, and the output layer will yield the final shape. So I just want to go through a short quiz just to reinforce some of the concepts we spoke about today. And I think about 10 questions here. So what is artificial intelligence? I'll kind of answer the question. It's a computer system which can simulate human intelligence. Which of the following tribe in machine learning is associated with deep learning neural networks? Again, we talked about 5 tribes: but the one we talked about is the connectionist, which deals with backpropagation. What is the function of the weight and the operation of a neuron? It reflects the strength of the connection between the neurons. Backpropagation seeks to minimize the error by adjusting the weights and biases. That's true. What is the function of the sigmoid activation function? Again, that's a nonlinear function, which is a damping mechanism, which yields an output which is more usable between 0 and 1. Again, a stable output is what we seek to achieve. Which the following is a correct choice for supervised learning? Again, we have labeled input data and specific expected outputs are known. The algorithm generates reasonable predictions for the response to new data. How does a neural network learn? Again, that's by adjusting weights and biases to reduce error. Again, we're trying to minimize error as quickly and efficiently, utilizing gradient descent, which is a mathematical calculus-based function. What is the essential mechanism for a neural network to learn? The answer is going to be backpropagation. Deep learning is a subset of machine learning. That's true. Again, we have the big AI, then we have machine learning, and then we have deep learning. So with that, I thank you all for your time. We want to provide a brief introduction to machine learning. We have a contact. Dr. Nguyen is again my mentor here. You can reach out to him with any specific questions. I thank you so much for your attention today.
Fantastic. Thank you so much, Dr. Gupta. No, that's a really great presentation. I'm really glad we got to touch on some of the concepts of the supervised learning, unsupervised learning as well. I got to see a version of this talk at SABI last year. That's how we connected for the first time, and with Dr. Nguyen as well. So I'm really glad that we could have this happen again, that you could come back and give this as part of our course. So thank you so much.
Yeah, thank you so much. It's been wonderful. I've really enjoyed our conversation over the past many months and the opportunity to be involved, and we hope to be involved in the future and to collaborate. And this has been wonderful.
Fantastic.